Okay, hello everyone. I welcomes to all in our lecture series on Dirac delta function. In this lecture series, we are discussing these topics. In our last class, we have been discussed introduction to Dirac delta function or physical interpretation of Dirac delta function. These topics are very much essential for B.sc, B.Tech, M.sc, M.Tech and various entrance examinations. In today's class, we are going to discuss our second topic, that is your representation of Dirac delta function and applications. So let us start. So these things already have been discussed. The physical significance of Dirac delta function, that is your introduction part of your Dirac delta function. Last class we have been discussed by considering a motion of a proton which will be interacted with a electric field. What is going to happen, that we discussed. Okay, in detail we have been discussed. So how the Dirac delta function will be represented at different points, suppose it is a gist, that how it will be represented, that also we have been discussed. Dirac delta function exists at x equal to a, it can be represented as like this. Okay, and how this equation will be written like this also we have been discussed in our last class. Along with also we have been discussed, if a Dirac delta function exists over a region or spreaded over a region, can be represented by a Gaussian function like this. Okay, and it has to follow this equation: minus infinity to infinity plus infinity delta x minus a has to 1, or minus infinity to infinity g means Gaussian function dx should be 1, and the typical Gaussian function represented as like this. So here the electric field which is spreaded over a region from this region to this region, this point to this point, can be represented by this function like this. The typical Gaussian function mathematically can be represented like this. In this class particularly, we are going to discuss the representation of Dirac delta function. So as here we saw that Gaussian function also can be represented as a Dirac delta function. That means Gaussian function has to follow this one, this equation, or minus infinity to plus infinity 1 by sigma root over of 2 pi e to the power minus x minus a square by 2 sigma square dx equal to 1. Here sigma is a constant, right? So here first we have to prove the Gaussian function can be represents the Dirac delta function, or Dirac delta function can be represented by by a Gaussian function. Then we are going to go for the some other functions which can represents the Dirac delta function. First we have to prove this one. Okay, so here you can see this term is a constant. I taken outside of this integration, remaining part I written as such, right? Then put x minus a by root over of 2 sigma as t. That implies root over of 2 sigma dt will be equal to dx. Okay, if we consider t equal to this much, try to find out the limits, new limits. So for x equal to minus infinite, if I will put over here, then t also will be minus infinite. If I will consider x equal to infinite over here, then t also will be plus infinite. Okay, so the new limits also will be your minus infinite to plus infinite, right? Now we have to just substitute these values. 1 by sigma 2 pi root over already is there, keep it as such. The new limits are minus infinity to plus infinity. So instead of here x minus a root over of 2 sigma, we consider t. So obviously this term will be written as t square, and dx will be written as this much, root over of 2 sigma dt, right? Okay, now here root 2 got cancelled, sigma and sigma got cancelled, so remaining will be 1 by root over of pi e to the power minus t square dt. Okay, so here this integration can be represented as a gamma function. For that we consider here 1 is there, so instead of 1 we can write t to the power 0. So As this is a even function, we can write minus infinity to plus infinity. Instead of minus infinity to plus infinity limits, we can write 2 into 0 to infinity. Then according to gamma function, we know if this type of integration we have, the value will be 1 by m, here x to the power n e to the power minus a x to the power m dx. If we have 0 to infinity, then its value is your 1 by m, 1 by a to the power n plus 1 by m gamma n plus 1 by m, right? Now just compare this integral with this one. Okay, we can found n value is your 0, a value is your 1, and m value equal to 2. So what will the value of this integration? It will be 2 by pi root over, already is there here, 2 by pi root over, and here 1 by m, 1 by m, 1 by m means 1 by 2, then 1 by a to the power n plus 1 by m. So here a is your 1, so 1 to the power n is your 0, 0 plus 1 by 2, gamma 0 plus 1 by 2, right? Right. So finally, how much we can get? 2 by pi root over is there, I written as such. Here 1 by 2, here 1 to the power anything is your 1, here gamma half is nothing but your root pi. So root pi got cancelled, 2 got cancelled, and we found 1. Hence here we proved that Gaussian function is the representation of a Dirac delta function. Okay. Now one beautiful thing that we can observe, if we are going to change the sigma value, if I will be increase the sigma value, here you can see the black color is belongs to sigma 1, red one is your sigma 2, and green one is your sigma 3. So as I am increasing this sigma value, this Gaussian function is spreaded over the space. But however, if I am going to consider for this case, for green one, integration for all this space means minus infinity plus infinity also we can get 1, and this for the red also 1, and for the black also 1. But as we are going to increase this sigma value, then the Gaussian function will be spreaded over the region. So this one you just keep in your mind. So here we proved that uh, Dirac delta function can be represented by a Gaussian function. Okay, so mostly this question asked in your exam 3 to 4 mark. This much you have to write. Okay. Now we're going to go for another function which represents the Dirac delta function, that is your rectangular function R. It exists at x equal to a, so it can be represented as delta x minus a, or R equal to delta x minus a equal to 1 by 2 sigma. The value is your 1 by 2 sigma in between minus sigma less than that of x minus a less than that of the sigma. Or we can write, if I will take minus a this side, minus a this side, the limits will be a minus sigma less than x less than a plus sigma. That means this point is your a minus sigma, and this point is your a plus sigma, and the middle point is your x equal to a, and this length is your 2 sigma, and the magnitude or this height is your 1 by 2 sigma. Okay, so this will be represents a Dirac delta function that we are going to prove, and elsewhere it is 0. That means x minus a more greater than sigma, then that means beyond this point, this side and this side, the rectangular function does not exist. Now we are going to prove that this integration from minus infinite to plus infinite has to 1. Very simple integration. Here you can see. So R, the rectangular function exists in between these two limits. So no need to write all the limits. So I written a minus sigma to a plus sigma limit. In between these limits, the function exists, and the value is your 1 by 2 sigma dx. Rectangular function value is your 1 by 2 sigma. Elsewhere it is 0. And this is a constant taken outside. Limit as such I written dx. Dx integration is your x, lower limit a minus, upper limit is your a plus sigma. Just substitute and we can found the value is 1. So here we prove that this rectangular function also represents the Dirac delta function. Now we are going to go for another function, this one, which represents Dirac delta function that we are going to prove. Okay. So here this function is your limit k tends to infinite sin k x minus a by pi into x minus a, where k is a real and positive. Okay. Now we have to prove this one. This function is the representation of Dirac delta function. Here you can see in this case at x equal to a, the peak value is your k by pi. How it is? Here you can see for limit x tends to a, that means when x tends to a, the value will be k by pi. How it is? Here you can see x tends to a, if I will put k x instead of x equal to a, then it will be sine 0 by pi into 0, x instead of x, if I will put a, then 0. So we can find 0 by 0 form. That means here we have to apply L'Hospital rule. Okay, if I will apply the L'Hospital rule for the numerator and denominator, what we can found? It will be cos k into x minus a into k divided by pi. Limit x tends to a. Now you just substitute instead of x a over here. So it will be 0. That means cos 0 is your 1. So we can find k by pi is the peak value of this function. Okay. Here you can see the peak value is your k by a. So graphically it is represented as this one. At x equal to a, this value is your k by a, k by pi, this value, and it will gradually decreases like this. Why? We know a sine theta is a sinusoidal function. That means it has to be like this, sinusoidal, symmetric to y-axis, like this. But this amplitude will gradually decreases due to this denominator factor. Okay, so as we are going to move from x equal to a towards right side and left side, the peak value k by pi will gradually decreases like this. So here you can see the maximum intensity of this delta function observed at x equal to a, and the intensity gradually decreases like this. Okay, so from the distance it seems to be a Gaussian wave function. Gaussian wave function is represented like this. So this is also like this. Okay, the upper part and the lower part itself, and it from the distance itself it is looks like a quantum particle. Okay. Now you just integrate this one. Pi is your constant, 1 by pi taken outside, and I rewritten numerator and denominator as like this. Here I multiplied 1k divided 1k. Sin k into x minus a, as such I written. X minus a is there, x minus a is there. Here instead of dx I written d of kx. D of kx is nothing but k into dx, as k is your constant, so only for that k I have been divided over here. Right. That implies this value will be equal to 1 by pi. Here you can see this k got cancelled, and other terms I have been written sin k x minus a by k x minus a into d kx. Substitute k into x minus a as t. So obviously k dx will be dt, or we can write k dx as dkx equal to dt. Substitute these values over here. That implies this will be equal to 1 by pi. Here this value is your t, and obviously this value will be t dt, because here d of kx equal to dt, right? And this is a very special integration which value always will be pi. So 1 by pi into pi equal to 1. Here also we proved that this function represents the Dirac delta function. Okay, now we are going to go for another function, this one, sin square kx minus a by pi kx minus a square. Here, if I am going to compare previous one, it was sin kx minus a, here sin square is there. Okay, so as we proved this one, third function, similar way you can prove this function also, very similar way. Okay, you do by yourself. Now fifth equation or fifth function, here you can say fifth function also represents the Dirac delta function, that is your 1 by pi limit n tends to infinite n by x minus a square plus n square. This one represents a Dirac delta function that we have to prove. Here k is a positive and real. Yes, I forgot one thing I have to tell to you, that here delta x minus a, here delta x minus a is your this one. If I am going to consider only delta x, or the so called delta x minus 0, that means instead of a I have to put 0. That means it will be limit k tends to infinite sin kx by pi x is the representation of delta x. That means delta x exists at x equal to 0. So if delta x exists at a, at x equal to a, then this will be the representation. Okay, so here delta x minus a, that means delta x or the impulsive force is uh, is exists at x equal to a. So only for that it is written as x minus a. If I am going to consider x delta x, that means delta x minus 0, that means this equation will be n by x square plus n square. So keep it these things in your mind. In this case, at x equal to a, the peak value will be how much? Infinite. Here you can see, if I am going to put instead of x a, so this value will be how much? This value will be 0. Okay, in this case, at x equal to a, the peak value is infinite. How it is? Here you can see, if I will put x equal to a over here, this part will be 0. 0 plus n square, so it will be 1 by n. Already limit n tends to 0 is there, so 1 by 0 equal to infinite. So peak value will be infinite at x equal to a. Suppose I am going to consider this is your x equal to a, that means delta function exists. You can say delta function exists at x equal to a certainly. Okay, other points it could not exist. So now we are going to prove this function will be the representation of the Dirac delta function. That means integration from minus infinity to plus infinity of this function will be 1. Here integration start, you can see 1 by pi. I am going to consider this function n by x minus a square plus n square dx. 1 by pi taken outside of this integration, 1 n by x minus a square plus n square dx. Here I just divided n square both the term of the denominator. What it will be? It will be 1 plus x minus a square by n square into n square, or you can say n square taken common from this term and written as like this, right? Right. So here n and n got cancelled. It will be written as 1 by pi minus infinity plus infinity 1 by this much. Here n is written as dx by n. Let us consider x minus a, this one, x minus a by n is your t. So that implies dx by n equal to dt. Just substitute, and limit will be same. Here you can see, if I will put minus infinity, t will be also minus infinity. If I will put plus infinity, so plus infinity minus a is a small value, so t also will be plus infinity. So limit is not going to change. So limit will be minus infinity to plus infinity. That implies, I'm telling you, that implies this much will be equal to 1 by pi. So here instead of this value, we are going to write t square. Limit is same, minus infinity to plus infinity, 1 by 1 plus t square, dx by n is your dt, right? Right. And this integration by considering gamma function, this value is your pi. So 1 by pi into pi equal to 1. So hence here we proved this function is the representation of the delta function. Okay, as I told, suppose it is exist at x equal to 0, That means delta x we have to write 1 by pi limit n tends to 0 n by x square plus n square. Keep these things in your mind, because sometimes in your exam it has been asked that this one n by x square plus n square is the representation of delta function that you have to prove. Okay, so these are the functions what we discussed are the representation of the Dirac delta function, or Dirac delta function can be represented by these functions, this one by this one, this one, and this one, and rectangular function and Gaussian function. Okay, now we are going to go for the application of Dirac delta function. This is applied for modeling impulse in physics and mathematics. The Dirac delta function is used to model impulse force or impulses which are tall, narrow spike functions. Okay, some of the example here you can see interaction of alpha particle with nucleus, that is your Rutherford experiment. That means if if I'm going to consider this is your alpha particle, when it is interacted with the nucleus of gold foil, suddenly it is scattered. Here you can see this particle, you can see it came with continuously and scattered suddenly at this point. Suppose this nucleus is at x equal to a, that means this delta function we can write as like this, delta x minus a. Okay, and if this moving helium atom sorry alpha particle is your fx, then this value will be f of a delta x minus a. These things already we have been discussed also. Interaction of water flux with an obstacle. Here you can see the water flux moving slowly. So when it is interacted with an obstacle at this point, it is deviated suddenly its path. So here one impulsive force we can imagine present over here, and the water particle interacted at this particular point and it is scattered. This situation also can be represented by the Dirac delta function. Representation of particle in quantum mechanics. Here you can see this is the particle. This envelope is your particle moving with a velocity that is your group velocity we know. And this particle, this envelope like this envelope is looks like a Gaussian wave function. Okay, this one Gaussian wave function, right? The upper portion Gaussian wave function, the lower part also Gaussian wave function. So this envelope or the particle of the quantum mechanics also can be represented by Dirac delta function. Representation of X-ray diffraction peak. Here you can see this is your X-ray diffraction peak. That means when the crystallographic plane interacted with X-ray and constructive interference is going to happen, the collector or detector will detect the maximum intensity. That means if the plane is present and interacted, collected by the detector, the maximum intensity will be present at that particular angle. So at this particular angle, the maximum intensity, at this particular angle, max intensity is there. That means suppose this angle is your this angle, suppose your 10 degree, and this angle is your 20 degree. That means at 10 degree and 20 degree we have here another peak also observed. Suppose here, suppose this is your 40 degree angle. So at 10, 20, 40, the peaks are can be represented by the delta function. Okay, the Dirac delta function here, when a car hits a concrete barrier and stops, the impulse or total momentum transfer can be treated as if it occurred at a single instant of time. That means this situation, this dynamics also can be represented by Dirac delta function when the car hit uh, suddenly with a barrier. The Dirac delta function can be used to represent the distribution of function on one or more random variables, right? Okay. Now, most important, unit and dimension of Dirac delta function. Here you just remember the Dirac delta function, that means delta x always has the inverse dimension, obviously corresponding unit of its argument. That means suppose x represents the length, delta x unit will be 1 by length or centimeter inverse, or its corresponding dynamic dimension will be m0 l minus 1 t0. Okay, likewise if we are going to consider x represents the momentum, suppose delta x will be inverse of momentum, or its unit will be inverse of kg meter per second. This one, you just remember this one. It is very very important. You can found in your exam mostly this question. Suppose if x, if a function represents the mass, then what will be its delta function in or unit of in term of delta function? It will be 1 by kg or kg inverse. Okay. Okay. So here we discussed in this class the representation of Dirac delta function with various functions and application of Dirac delta function. In the next class, we are going to discuss properties of Dirac delta function and corresponding properties of Dirac delta function and their proof with important question of the corresponding properties. Thank you so much for watching this video. Thank you.